All right, today we're going to take a look at first order linear differential equations, and it's our last section of differential equations. If differential equations is a topic that you've enjoyed, we do have a class that is just differential equations here. And I know some of you have talked to me at different points about math minors, or a couple of you have math majors and whatnot anyway. But differential equations is a really good course, and this sort of gives you a little bit of a taste of what that looks like. So we have one more section we're going to look at today, and these are linear differential equations, first order specifically. So I'm going to talk first about what they are. So a first order linear differential equation is one of the form dy dx plus p of x y, or p of x times y equals q of x. And you should sort of, looking at this, see why in the world it's kind of called what it is. Can you see a little bit of this sort of y equal mx plus b form to it? We have a component multiplied by y. We've got another component added to it. It has sort of the same feel to it as a linear equation. And it's first order because I'm only doing a first derivative. P and Q are continuous functions, and this is the standard form for this equation. Okay? All right, so I want to talk about how we go about solving a first order linear differential equation. First, you put it in standard form. That sounds obvious, but sometimes you can deal with things without standard form. Of course, standard form of a line itself we hardly ever use. But for this one, we start out in standard form. The next thing you do is you identify what p of x is and you integrate it. And then that p of x value integrated, notice it is the exponent of e on step 3, right? And that equation, where it is the exponent, is called u of x. And once we have that, we're going to integrate again, but the integration is 1 over that new value u of x times the integral of q of x, which you would have identified basically back up in steps 1 or 2, times u of x. So it looks like you're putting a u of x inside the antiderivative and one on the outside as division on the antiderivative. And then this will find the general solution for your first order linear differential equation. All right, I think most of you have everything written down. So we're going to do one, because that seems like a next natural approach. All right, so our form that we're looking for is a form where we have the derivative, like y prime, right, plus or minus a function times y equal to some other function. And if you take a look, this is actually already in standard form, right? We have the derivative y prime. Our p of x is going to be whatever's multiplied by y, in this case not real interesting, but it's there. And then our q of x is the number that's on, in this case number, that's on the other side of the equation. So this is already in standard form. So step 1's rather already done, except that we are going to identify what p of x and q of x are, and since we're working in step 1 anyway, I'm going to do it right here. So step 1, what will p of x be? I know that's part of step 2, but not quite. -1. You see, the y is part of the form, right? It's part of the formula that we had over here. So, let me turn one back. The y that you see right here, Cameron, is actually in the formula. It's the number that's multiplied by y that's p of x. Okay? All right, so it's actually -1 on this one. And what is q of x? Because we're going to need it later too. It's 16. So we've got some wonderful constants, and I don't know about you, but taking derivative of constants is something I'm pretty good at. I think y'all are too. So we're going to get to do that on this one. All right, so that's step 1. Step 2, we're going to take the antiderivative of p of x. So our p of x is -1. And what is the antiderivative of -1? Negative x plus c. Thank you. Now, we're not going to end up needing the plus c for the formula as we keep going, but I'm glad you mentioned it because Cameron mentioned it at the beginning too, this sort of plus c issue keeping coming up. So for what we're working with here, we're not going to need this piece of it, but let's keep going so you can see what happens. All right, the next piece that we're going to do, step 3, is we're going to identify what this function u of x is. And u of x is found by taking the base e raised to the answer we got on step 2. So in this case, e to the negative x. So far, so good? We haven't really done anything super taxing yet, agreed? Okay, it's a little awkward maybe, but not difficult math. Now let's keep going, because the last step, step 4, is actually us taking the antiderivative of this other form. So the form is 1 over the u value, which was e to the negative x from step 3, times the integral of the q equation, which we did back up on step 1, which was 16, times the u equation from step 3, which was e to the negative x. And it has dx at the end. Now, do not be tempted to think that somehow you can transfer the e to the negative x on the outside inside, because if you did, you'd cancel them, which would obviously defeat what's going on. Agreed? I mean, we put it in there in the order that it is for a reason. The one that's on the outside stays on the outside, and the one that's on the inside stays on the inside. However, we can integrate this. So the part that's on the outside, again, stays on the outside. Yes, we can. We will later. If you want to do it now, I'm happy to do it now, though. Yeah. So how would you like me to write it, Cameron?
Just e to the x.
Yeah. Since it's e to the negative x in the denominator, you can't write it e to the x on the outside. That's fine. All right, now we need the antiderivative of 16e to the negative x. What's that's antiderivative?
Negative 16 to the negative x.
Right. Plus c. And it does matter here. You'll see why here in just a second. You see, at this point, what we have is we actually have a distribution issue, correct? I've got e of x on the outside, e to the x on the outside of something that's added. So I will have to distribute, and it is not the same to add the c on at the end because of what you're about to see next, okay? So what you're seeing happen here is that this e to the x gets multiplied by the negative 16e to the negative x, and what does that become? It becomes negative 16. And if you would have left it in the denominator, it might have been a little bit clearer to see that one's division and the other's multiplication. But again, we can add the exponents and it works too, right? Positive x, negative x is 0. E to the 0 is 1. Thank you. So this is just negative 16. The other piece, however, is c e to the x, right? And this function at the end right here is the general solution for my first order linear differential equation. All good? All right. We're going to do another one, because the first one was just only a little bit fun, but it had lots of constants in it, and you don't see near as many constants this time, do you? No, in fact, it does not start out in the standard form, does it? So we're going to have to work a little bit to get it there. So what am I going to do first to get this into standard form? Okay. Like that, Cameron? Okay, now what? I think that's a good next step. Now what? We don't want everything to move. Take a look back at the very, very top of the first page. We want the dy dx on one side, and I know it's on the opposite side of where we want it. We can switch that around, though. So if you would prefer, we can write this right now as dy dx equals y plus 1 cosine x. That's perfectly fine.
How would you distribute the cosine x?
All right, so if we distribute cosine x, well, look back at your function over here. What is your goal? Your goal is to get the y on the left-hand side, right, with the dy dx. Do you guys see that form back here on the front page? So Cameron's got the right idea. We want to distribute it because I don't really want all the component with y. I just want y alone. So we are going to distribute that next, like so. So far, so good? Then what? Go ahead, Hannah. Right, so I can write this as dy dx minus y cosine x plus cosine x, I'm sorry, not plus, equals cosine x. Is everybody good with that? You see how that satisfies all the condition we needed it to back on the front page? First slide. Okay, so let's identify right here, and we'll do it out to the side. What is p of x? Negative cosine x, and of course I don't have it written in quite the right order, but I'm happier to leave it written with the y in front, simply because I don't want you to think the y is multiplied by the x. So either leave it written this way, or I suppose you could do this if you'd like. You could write minus cosine of x, and then put the y in parentheses to understand, or the cosine of x in parentheses to understand that the x and the y aren't multiplied. All right, so yes, p of x is negative cosine of x. What then is q of x? Cosine x. It's what's on the right-hand side, yeah? Okay, so somebody tell me, see if you can tell me without looking, if you're not already looking. What's step 2? Close. Antiderivative. And of what? Yes, the p of x value that we just identified, right? So step 2 is to take the antiderivative of, in this case, negative cosine of x dx. So what is the antiderivative of negative cosine of x? All right, negative sine x. And we don't need the plus c for this portion of the work, okay? So if you want to write it now, that's fine, but you're not going to continue using it in a moment. Okay, so that's step 2. Step 3 is to do what? We're going to identify u of x. And u of x has the e component, doesn't it? With an exponent of, right, the answer to part 2. So that's why we did part 2, is so we could use it here. So negative sine of x. And then we're done. That's step 3, right? We just rewrite this little piece. All right, so step 4 then is our last step. It is generally the longest step. And it's the part where we're sort of piecing all this back together, okay? So part 4 is going to be y equals, we take 1 over, and I'm going to write it as 1 over for the now, the u of x that we got on step 3. So e to the negative sine x. And then we've got an integral. Our integral has cosine in it next because that's my q of x equation. Q of x was cosine of x times u of x, which was e to the negative sine of x dx. Is everybody good with all those pieces? Okay, now what? How are we going to do that? So we're going to use substitution, right? You bet. So if u is negative sine x, what is du? Okay, so Cameron, can I rewrite the first piece outside of the antiderivative symbol? I can, right? How am I going to write it? Not Cameron, somebody else this time. How could I rewrite that if I wanted to? Right. So e to the sine x, you don't have to rewrite it here. At some point you're going to rewrite it, but so I'm just going to rewrite it here now. I'm going to change my substitution, or I'm going to do my u substitution now. So my u substitution is going to introduce a negative, right, because I don't have a negative in the problem currently. So I'm going to put that negative just in front of the e to the negative sine x out in front so it's not bothering me with making me think it's subtraction or something like that, because it isn't. And then this is the antiderivative of e to the u du. Is everybody good with that? Okay. So we've got negative e to the sine x. What's the antiderivative of e to the u? Right. Plus c, thank you. And then we need the u put back in, yeah? So negative e to the sine x of e to the negative sine of x plus c. Okay, so what happens when you distribute this? Because this is at the same point we were last time. We get to this point, we distribute. So what happens when we distribute this?
You get -1 minus c to the sine of x.
Okay, so the e sine x and the e to the negative sine x, those two pieces are 1 because they're reciprocals of each other. One has a positive exponent, the other negative. And then one on the outside's negative, so I've got -1. And then I'm going to distribute the e to the negative e to the sine x through to the next piece. So the negative is going to come along. I'm going to get the c from the next piece, and I'm going to get the e to the sine x from the first piece. And I have my second solution of today. First solution for this problem, of course, but this would be the general solution for this first order linear differential equation. Okay, is the process starting to feel a little bit less weird? We're just following a series of steps. All right, what's different about problem number 3? Well, I mean, it's problem number 2, but what's different about example number 2 here, the third problem we're going to do? It does have a condition, and what does that mean for us?
You find the particular solution at the end.
Yes. So everything's going to be the same until we get to the end, right? And then at the end, we're actually going to be able to find C. Agreed? Okay. So somebody tell me, see if you can do it without looking. If you can't, it's okay. But tell me what step 1 is. What do I have to do first? Get it in general form. But it is. This one already is, isn't it? Yeah, it is in general form already. So this one's already in the general form that we need, or standard form that we need. So let's identify at this point then what is P of x and Q of x. So what is P of x? Good. Tangent x. And what is Q of x? Great. Okay, step 1 done. Awesome. Step 2, what do I do next?
Take the antiderivative of p of x.
Yeah. So the antiderivative of P of x, well, which is the antiderivative in this case of tangent x dx. Okay, so tangent x is one that you may have not in the tip of your memory because we haven't dealt with it or used it much as of late. But you had to learn it at one point because you did it for me on a basic skills quiz, right? And it's in the front of your book, which you can reference when you need to on the test too. So what is the antiderivative of tangent x? And Cameron, I'm going to call on you since you flipped to the front of your book.
The negative ln cosine of x.
Is the cosine of x an absolute value?
Yeah.
Okay. And then
Plus.
we would have plus c, but we're not going to be using the plus c for the continuation of the problem, so we could leave it off at this point. Okay, is that all right? Interesting things are about to happen. What's step 3? Right. U of x is found by taking, do you know, Dylan? The next step? How does step 3 relate back to step 2? Kendra? We do e, and then it's to the power that we had in step 2. So negative natural log, and then cosine of x. Can that simplify? Yeah, it can. But we need to move something. What do you want to move?
Negative.
Okay, so where's this negative going to move, Cameron?
So we can put power.
It's going to kind of power on cosine, isn't it? All right, so let's take a couple steps to think through that. I'm going to have e to the natural log. That piece is going to cancel itself out in a moment. And I'm going to be left with the cosine of x to the negative 1, right? So this is cosine of x to the negative 1. What is cosine of x to the negative 1? It's secant. So on this problem, we don't actually end up with antiderivatives with e in them when I get to step 4, do I? That's simplified. I'm dealing with trig functions only on this particular problem. All right, so step 4 then. Step 4 is where I set up my antiderivative in the specific form, where I do 1 over step 3's solution, which was secant. Yeah, we'll simplify this piece again to cosine in a moment. And then I've got the antiderivative of q of x. Q of x, way back at the beginning, had 2 pieces to it. It had secant x plus cosine x, didn't it? So that's q of x. And what do I take inside with q of x? Okay, sorry guys. I had already turned that off, but all right. So what goes after this piece? U of x, which was secant of x, right? And then I've got dx. All right, so Cameron mentioned that I want to change the 1 over secant at the beginning to cosine x, which sounded good to me. Now what else do I need to do? Now what?
Distribute secant of x on the inside.
Okay. So if I distribute this, secant x times secant x is secant squared x. Cosine x times secant x is 1, because they are reciprocals. We're not done with the fun. Because what is secant squared x plus 1? That's tangent. Yes, it is. Good job. And do you know the antiderivative of tangent of x? So that's tangent squared. Get my tangent squared in there. Okay. Try one more time. Do you know the antiderivative of tangent squared of x? Oh, I don't know if I want to do that though. It is equal to tangent squared of x, but I don't think that's helpful in this case. I jumped the gun too. I think I'd rather pause right there, and I'd rather separate this. Watch this then. Because we don't have, well, we do have a way to deal with tangent squared, but we did it in Chapter 8. With Chapter 6, we don't have a direct way of handling that as of yet. But I can separate this antiderivative, can't I?
Yeah.
And that's actually friendlier anyway. Because the antiderivative of secant squared,
It would be 1, not x.
oh, I already went ahead to my answer, didn't I? I'm just excited to finish the problem. All right, let's try again. How about the antiderivative of secant squared then? That's tangent. Thank you. And then the antiderivative, even when I rewrote it wrong, didn't I?
Yeah.
Are you guys laughing at me behind my back? Well, no, in front of my face, actually. How about the antiderivative of 1?
How do you say that was wrong?
What's wrong?
Before I was trying to tell you that
Oh.
x was wrong, but it's x.
Oh, I almost forgot something. plus c. Okay. We're getting close to the general solution, which isn't exactly what I was asked to find, but we're still getting close. I've got cosine times tangent. That is sine x. And if you don't remember or think through why that is, remember that tangent is sine over cosine. So when we multiply sine over cosine by cosine, the cosine is going to cancel. So this is going to be sine of x. And then I have x cosine of x plus, unfortunately, c cosine of x, which just looks like I forgot to write my c and I wrote it twice or something. Right? Not forgot. I duplicated my c, but I didn't. It's really supposed to be there. All right, so this is the general solution, right? But I was not asked to find the general solution. What I was asked to find?
What C equation where it equals?
Right. They call it a particular solution, and it's got an initial condition given, or a boundary condition is what they've phrased it in this particular problem. So if you take a look, the initial condition or the boundary condition says that y of 0 equals 1. All right, so what am I going to put in and where? What does y of 0 equals 1 mean? Y is 1, and x is 0. So this is 1 equals sine 0 plus 0 cosine of 0 plus c cosine of 0. Okay, so let's remember some of your trig. What is sine of 0? 0. What is cosine of 0? It's actually 1, but there's a 0 times that 1. So this piece is also 0. And then I have c times, and we just said cosine of 0 was 1. So we found out that c is actually equal to 1. So our solution from the original problem, our particular solution down here now, written out entirely, is y equals sine of x plus x cosine of x plus cosine of x. And there is one other way we could write that simplified, and that's simply to take a look at the fact that we've got two pieces that have cosine in them, and if you wanted to, let me show you on this screen. I didn't intend it to be on this screen, but we could take the y equals, we can write my sine of x, and we could factor out the cosine of x, and write this as 1 plus x, or x plus 1. I don't really care whether you do this step or not, but the back of the book is going to probably do something like that when it has an opportunity to do so. If you leave it in the last form we have down here at the bottom, that's okay too. Not really so sure that this really looks any simpler than the previous slide. Is it all good? All right.